Hi friends, welcome to our channel. Let's have a look at problem 790, Domino and Trimino tiling. In this video, we're going to explain a solution based on mathematical induction. So I'm going to use a figure by this leetcode user. So here we are given two types of tiles. One is 2 by 1 and the other is like this, Trimino, right? So we want to give an integer n. We want to return the number of ways to tile an 2 by n board. So we need to return the answer modulo this prime number. So here are two cases. When n equals 1, so it's the 1 configuration. When n equals 3, there are 5 configurations. So first, before we do the analysis, I want you to notice that 10 to the power 9 plus 7 as an integer is actually a prime number. So this is good to know, right? So next, we want to derive a recursive formula using mathematical induction. So here I'm going to use some joining by this user. It's HD 5870, right? So here we consider the n and the number of configurations. So here dp corresponds to the f here, and just for convenience, you can understand it as a function relationship, right? So if n is 0, right? But in this problem, the n is greater than or equal to 1, but we want to have this because no configuration, so or just you can assume it to be 1. When n equals 1, you could have only one vertical domino, so you have 1. When n equals 2, you have two possibilities, 2 vertical domino and 2 horizontal dominoes. So you get 2 configurations. So when the n equals 3, so you can consider the first last one. So it were a vertical one. Then you have 2 configurations, that is 2 vertical dominoes or 2 horizontal ones. This is the one case. Another case is that the last 2 columns are 2 horizontal dominoes. You have only one possibility, that is a vertical domino. So here, notice that we could no longer consider the last one ending at a vertical domino because those will be covered by these 2 cases, right? So when you have the last 3, if you have 2 Triminos, so these are the 2 configurations. So overall, you will get dp2 times 1, and dp1 times 1, and dp0 actually times 2. So this is for dp3. And for dp4, you can do the same thing, right? If the last column is a vertical domino, you should multiply this by dp3, right? And then if the last 2 are 2 horizontal dominoes, you should multiply by dp2. If the last 3 are 2 Triminos, these are the 2 possibilities. And then 4 minus 3, that is 1, you should multiply by dp1. So if you have 4, so you have 2 Triminos and 1 domino. So these are the 2 configurations. You get to multiply by dp0 because 4 minus 4 is 0. So by now, hopefully you have seen the pattern. That is dp4 equals dp3 plus dp2, then plus 2 times dp1 and 2 times dp0. Let's look at dp5. So if the last one is a vertical domino, so you should multiply by dp4, right? Because 5 minus 1 is 4. If the last 2 are horizontal dominoes, you should multiply by dp3. Again, as I emphasized, you could no longer consider 2 vertical dominoes because those is covered by this case, right? And then if you have the last 3 columns, there's 2 configurations based on 2 Triminos. 5 minus 3 is 2. You need to multiply this by dp2. Then there's the 4 configuration, 4 column configuration. So 2 Triminos and 1 domino. Still 2 possibilities. And the 5 minus 4 is 1. You should dp1 times 2. So if you have 5, you have 2 Triminos and 2 dominoes. Those are the 2 configurations. So 5 minus 5 is 0. You need to multiply by dp0, right? Let's first ignore those numbers because those numbers are very easy to compute once you get the recursive relation. So in the figure, the author also draws the dp6. And then what he get actually is this. So dpn is dpn minus 1, dpn minus 2, then plus 2 times dp n minus 3 up to dp0, right? So those will be the generic recursive formula. So I guess we should now we can ignore the figure for a moment. So I'm going to use f as that dp, or you can say this f is a function or maps the integer to the number the returned or number of configurations using Domino or Triminos. So the recursive relation is this: fn is fn minus 1 plus fn minus 2 plus 2 times the sum running from fn minus 3 up to f naught, right? This is the star. So you can actually here we want to show fn is like this, or more precisely we want to show fn is 2 times fn minus 1 plus fn minus 3. So here we can assume this holds up to n, right? And then we show this holds, right? Or this holds for n plus 1. So this is the mathematical induction. So it's also known as the second induction method. So here if we write fn plus 1, it would be, according to this formula, it will be fn plus 1. And then here we have 2 times fn minus 2. So I write 1 here, put it in the this bracket, and then I get another fn minus 2. Then plus 2 times fn minus 3 up to 0, right? This part. Then by our induction hypothesis star, right? So we can know this sum of fn minus 1 plus fn minus 2 equals this fn minus 2 times this tail, right? So here I write here fn minus this tail, that is this bracket, right? And then we should plus this fn minus 2, then plus this 2 times the tail. But now something magic happens. So this bracket thing, and in the tail is minus, but here the tail is plus. So those two cancels. So you have fn here, you have fn here, you have 2fn, you have fn minus 2. So this is for fn plus 1. It means that once we assume this holds up to n, then fn minus 1 will also hold, right? By mathematical induction, this is a valid formula. Therefore, in general, this will be the formula. So once we have this formula, then writing the code would be very straightforward. Let me quickly code that. First, we have this mod is 10 to the power 9 plus 7, right? And then if n is less than 1, let's just write this, because actually here n is greater than or equal to 1. So we just return 1. If n equals 2, right? So we can return two possibilities, right? So 2 vertical dominoes or 2 horizontal dominoes. So then if n equals 3, we also know the result from this example, that is 5. So now let's look at the generic case. So here I'm going to use dp0 times n plus 1. So dpi will be the return for the integer I. But here, if I initialize like this, I'm using on space, but it's very straightforward to make it o1 space, right? So we set dp0, dp1, and dp2, and dp3 to be 1, 1, 2, 5. And then we're going to iterate, right? So for I in range, so 4 up to n plus 1. And then what we do, so dpi equals, so 2 times dpi minus 1. Because our I is starting from 4, so this I minus 1 is at most 3, so it's already initialized, so it's okay, right? So dp I minus 3, because I is greater than or equal to 4, so this actually is greater than, I minus 3 is greater than or equal to 1, right? But here, let's do not forget to modulo this one by a constant. And then we just need to return dpn. So this will be the full code for this problem. Now let's run it. So here module, so just delete this part. Let me directly submit. list assignment index out of bounds. Let's see. So here n-1. So dp. I guess this is due to here, right? Let's see. And less than or equal to 1. Yeah, I guess we should include the case for 1. Now let's submit that. Yeah, it passes all the cases. So actually for this problem, there will be a very complex explicit mathematical formula, but I don't think that will be a thing we need to pursue. But here for our video here, on one hand, we derive the general formula using mathematical induction. On the other hand, we practiced dynamic programming. I guess I will content ourselves here with this explanation. So with that said, I guess that's it for the current video. Thank you for watching.